Hello, this is a part of Microgrids, Smartgrids, and Supergrids course developed within Essence project, namely its Part 2 Microgrids. The content of this part has been condensed to provide you some essential things that might be useful for the summer school case assignment. The course targets the following learning outcomes that we hope you will obtain and improve within the course. These outcomes are to analyze grid configuration, define pros and cons, to design appropriate system configuration based on the stakeholders' goals, and to solve network reconfiguration tasks for a microgrid. So the course is structured in the following way. We are going to talk about microgrid goals, main components and structure, then about microgrid operation, network reconfiguration, and also a practical task about grid reconfiguration will be explained. So let's start with microgrid goals, main components, and structure. The microgrid concept is originated in late 90s thanks to the European and US engineers and scientists and was associated with a growing number of distributed energy resources, which increasing share could impact large system reliability to which they were interconnected. The other important motivation is to ensure reliability and resilience in case of natural disasters, physical and cyber attacks, and cascading failures in power systems. Since that time, the definition of microgrid includes three major requirements. The microgrid boundaries shall be clearly defined. Usually, there is one point with main grid coupling. The resources within microgrid shall be controlled in a coordinated way to meet internal goals of microgrid. The microgrid shall be able to operate in parallel with and independently from the main grid. Size of microgrid isn't limited by its definition, but since it's a part of a distribution grid, its capacity is limited by the transfer capability of the lines and power transformers. Besides, the interconnection requirements in different countries clearly define a maximum size of distributed energy resources that can be connected to the utility grid. Since a microgrid is considered as one object representing a group of distributed resources, its maximum size can be from 10 kVA to 10 MVA. It is usually noted, as you may see from the example of connected requirements on the slide, that the size is limited by the capability of distributed resource to impact utility grid. Microgrid can be considered as a small-scale version of the traditional utility grid that is better able to optimize energy services through its intelligent controls, designed to feed the specific needs of the energy users community may serve. Unlike traditional utility services, the ability to coordinate unique community energy needs with generation resources can make a microgrid a superior choice. The goal of a microgrid is usually defined by the motivation of the community to which it serves. As you may see from the slide, the main stakeholders may be different from urban communities to military base or industrial enterprises. However, the main goal remains similar: fuel independence and cost savings, as well as a reliable and independent power supply. The microgrid boundaries shall be defined in respect to how many loads can be supplied by local energy resources, and goals solved within these boundaries, like integration of distributed resources, support of critical loads, reduction of losses, improved voltage profile, etc. As you may see from the slide, the source connected to the bus of distribution substation and serving to all of the feeders can form full substation microgrid. While connected close to exact consumer and covering their own needs, it may form single customer, partial, or full feeder microgrid. The microgrid consists of the following main components: energy generating sources that are represented by a variety of different technologies. The main feature is that a primary source of energy shall be locally available. Controlled loads, which consumption level can be adjusted in respect with demand response programs or energy efficiency measures when necessary. Energy storage, which is necessary in case of non-continuous availability of generating resources, and energy management system, which task is to collect the information from all actors and establish the reliable and optimal operation as an integral object. So corresponding information channels shall be established in respect to the control strategy, which can be centralized, decentralized, or distributed. As already mentioned, generating resources, power and microgrid may be of any nature. Of course, the most favorable are renewable sources, like photovoltaic modules, small wind turbines, mini hydro, and biomass-fired small-scale combined heat and power plants. However, non-renewable sources, like fuel cells and fossil fuel-fired diesels and microturbines, might also be used. Most popular today PV and wind generators have the following specifics. They have stochastic, variable nature. Thus, accurate forecast technologies are required to ensure energy balance in microgrids. Otherwise, strong connection with utility of much larger size that may compensate renewable energy variation is necessary. Interconnection of renewable sources and grid-following inverter also change the system dynamics and complicates parallel operation in case of grid faults. These two particularities limit a share of PV and wind generators and require additional studies to define the maximum penetration level. When engineering microgrid, it's necessary to keep in mind that different power sources may have different interfaces to connect with AC grid or alternating current grid. As just discussed, PV panels require to step up the DC output and then convert voltage into AC. The rest of generators are electrical machines, but depending on the frequency of the primary mover, they also might be equipped with power electronic interfaces. Storage devices include all of electrical, pressure, gravitational, flywheel, and heat storage technologies. While the microgrid concept focuses on the power system, heat storage can be relevant to its operation. For example, availability of heat storage will alter the desirable operating schedule of combined heat and power system, as the electrical and heat loads are decoupled. Similarly, the cooling or heating of buildings will alter the load shape of heating, ventilation, and air conditioning system, and therefore the requirements faced by electrical supply resources. The batteries may help to balance fast-changing loads and variable sources of microgrid, thus allowing a standalone operation. However, the runtime is limited due to their limited capacity, and due to the relatively high costs, the expediency of the application shall be confirmed by feasibility study. Controlled loads are particularly important to microgrids simply by virtue of their scale. In small power systems like microgrids, load variability will be more extreme than in utility-scale systems. Thus, load control may be a valuable tool for energy balancing. Load shedding is not a new mean for power system balancing in case of emergency situation, but with increasing share of smoothly and fast controlled loads, the consumers may contribute to system balancing without power interruption. Generally, microgrid is connected to the power delivery system at a point of common coupling, thus appearing as a controllable single subsystem to the utility grid. Microgrid can be designed to operate as direct current DC, alternating current AC, high-frequency alternating current HFAC, or combination of three of these. Many new distributed energy resources are direct current, like photovoltaic generation, batteries, and fuel cells. Also, many high-efficiency loads are also DC. Utilizing a DC bus in microgrid may avoid many of the power conversions required when using an AC bus, potentially leading to higher energy efficiency, loss reduction, and improved economic operation. Besides, the DC bus also isolates the microgrid from the utility regarding power quality, frequency, voltage deviations, and harmonics. There are three types of converters: boost converter, main converter, and bidirectional converter that share a common DC bus. The bidirectional converter is DC-DC converter. It's designed to maintain the stable DC bus voltage through charging or discharging the battery when the system operates in the autonomous operating mode. A boost converter or step-up converter as DC to DC converter that step-ups voltage while stepping down current from its input supply to its output load. And main converter interfaces DC bus with AC grid. In case of AC microgrid, all distributed energy resources and loads are connected to a common AC bus. DC generating units as well as energy storage will be connected to the AC bus via DC to AC inverters, and AC to DC rectifiers are used to supply DC loads. The three possible network configurations are radial, ring, and mesh connections. A radial connection among microgrid components is simple and easy to implement. This configuration also needs easiest protection plans. Ring topology is more complicated than radial configuration as it provides multiple paths of flow of current. Protection strategy also requires advanced features. The most complicated topology is mesh configuration. This configuration has multiple connections between microgrid components, thus have multiple options of power distribution. This complex architecture requires comprehensive protection techniques to ensure reliable operation of microgrid. To gain additional benefits from power exchange, microgrids can be clustered or interconnected through the AC grid or DC hub. There are many ways how to do that. As an example, parallel connection is shown on the slide. Well, by the moment we discussed four aspects of microgrid classification. Let's sum up. It's type of current, type of source, scenario or customer needs, and size. The next aspect that we are going to discuss concerns microgrid operation. Well, let's proceed. Power system operation is based on two milestones, reliability and economic efficiency. So the reasons of microgrid connection to the main grid are also associated with these milestones. As regards reliability, multiple generators of main grid have a reserve capacity, act as additional source or slack bus for microgrid. So direct connection of AC microgrids to a large power grid facilitates stable operation, but only if the power grid is much larger and able to maintain stable voltage and frequency in case of disturbances. When using renewable energy sources, a grid connection may also reduce the need for energy storage in the microgrid. If not all loads in a microgrid are critical, a grid connection may allow to reduce the investment in local generation. Well, regarding the economics, the microgrids are typically planned with extra capacity with respect to the local load. This extra power capacity can be injected back into the grid in order to obtain some economic benefit. And also, the grid connection allows reducing fuel operation costs by utilizing power from the grid at night when electricity costs are low. There are two basic operating modes, grid-connected and islanded. Let's speak about grid-connected operation first. Grid-connected operation may be continuous or temporary. During normal grid-connected operation, the microgrid is continuously connected to the grid and the loads are powered by a power mix of grid and distributed energy resources. This mode is the most reliable if connected to the large system. The grid-connected operation may also be established due to the scheduled equipment maintenance of normally islanded microgrid for some period of time, like minutes, hours, or even days, when remaining distributed energy resources are not able to cover microgrid demand. If a transfer from islanded mode to grid-connected is required, a synchronization conditions shall be established. Connection to the main grid is also required in case of internal microgrid faults. If the operating conditions are not permissible after fault clearing, connection with the main grid is required to save critical loads. If it's too late and microgrid blackout occurred, connection with the main grid is established without synchronization, since microgrid generation is off. However, recovered distributed energy resources shall be synchronized individually later. Well, as regarding island operation, during island operations the microgrid system is not connected to the grid and the load is powered by distributed energy resources only. The islanded mode can be normal if islanded microgrid is able to self-balance and doesn't require external source. Such mode can be preferable to avoid bidirectional power flows and allow using simplified protection schemes. Islanded mode can also result from external grid disturbance or loss of utility interface due to the disaster. If microgrid's own generation is not adequate to supply the load, then part of the load, non-critical load, will be shedded. In such case, transfer from grid connected to islanded mode is done automatically by means of protection and a main switch. If island operation is possible and microgrid can self-balance, such conditions are called intentional islanding. If islanded operation is forbidden but happen, this is called unintentional islanding, which shall be detected and eliminated. So the key differences between grid-connected and islanded operation consist in organization of control scheme. In case of grid-connected operation, main system variables like voltage and frequency are maintained by the utility controller through activation of larger system reserves. From an economics point of view, the goal is the same, to minimize costs, but in case of grid-connected operation, there is more flexibility since wholesale prices may be lower during low demand hours. It's much easier for large and strong systems to compensate variation of renewables. It acts as slack bus in respect to microgrid. In case of islanded operation, there is a need of proper planning of microgrid capacities and forecast of renewables to decide on the required size of reserves. So it's clear that grid-connected operation has many benefits for the grid, and it's preferable to consider it as normal operation mode for microgrid. The islanded operation of microgrid is complicated due to the comparable size of loads and generating sources. Thus, normal load variation causes much larger imbalances in microgrid than in utility grid, and thus put additional requirements of the distributed generation control. For example, when the load changes rapidly, it's necessary for the distributed generators to adjust the output with larger speed. They shall have, in other words, a higher ramp rate. If generators cannot match the loads promptly, this may result to instabilities of system variables like voltage and frequency collapses. This problem is especially urgent for variable resources since the maximum output depends on the availability of primary resources like sun, wind, and etc. Thus, to maintain stable operation of systems with large share of such generation, energy storage systems are required. Energy storage main job includes peak load shifting and shaving. Let's discuss what is a peak shifting based on the picture on the slide. It seems that the demand varies a lot during the day. The peak demand happens around 7 p.m. and may last about 2 hours. But in the morning before 8 a.m. the load is very low. Thus it's possible for energy storage to store energy in the early morning and release the energy supply, the microgrid, in the early evening. Load curve shaving is useful to reduce the influence of the load variation and lower the costs of the microgrid, such as the cost associated with advanced forecasting, control, ensuring fast response speed reserve of generation, and etc. The original load in the figure is fluctuating constantly due to the switching on and off of the devices in the system. With the help of the storage, the sudden increase and decrease of load can be compensated. The resulting load curve can keep constant for a certain time interval if the mean value of the load doesn't change too much. But it shall be noted that energy storage capacity is quite expensive and has limited runtime. Thus, it's wise to define an appropriate combination of different distributed sources to achieve microgrid goals. Well, let's discuss specifics of the use of different distributed resources. We start with conventional generators with controlled output. If we consider a standard distribution grid with no distributed resources, the load is supplied by the utility grid. But if we lose the grid connection, the load is fully de-energized. If we add conventional distributed source with the size adequate to supply critical loads, in case of islanding, it may also be operated during normal conditions to cover base load and hold speed reserve. When the microgrid turns in islanded mode, the generator is loaded up to its max limit to supply the critical loads, and the rest of consumption shall be disconnected to ensure real power balance. The disadvantage of this case is that in case of sudden increase of the load remaining online, the generator will not be able to compensate this imbalance, and frequency will drop with a speed proportional to imbalance. Thus, it's necessary to match the capacity of distributed generator and max critical load carefully at the planning stage. If we want to benefit from variable renewable source, then in case of grid-connected operation, its output fluctuations will be covered by the utility. The microgrid will be seen from the utility side as load fluctuating in response to the change of ambient conditions. But in case of loss of utility interface, the microgrid will be fully de-energized if the variable source has grid following inverter because of the loss of utility voltage. And even we have more expensive grid forming inverter used for connecting variable energy source. The output of variable energy source doesn't allow adequate system balancing and stable operation of the system because it changes in respect to the weather conditions. In case of controlled alternative energy source like fuel cells with grid forming inverter, the drawbacks are the same as for conventional generator loaded up to its max output, except of much higher capital costs. Quite evident solution to secure critical loads in case of grid operation is to install energy storage. In case of grid-connected operation, the storage charges up, which increases load consumption of microgrid. And when microgrid goes unlit, storage releases energy to supply critical loads. The drawbacks of this scheme is that energy storage has limited runtime, and the longer runtime we want to ensure, the larger capacity and higher costs are required. To integrate variable renewables into microgrid and allow it to work in a stable manner during off-grid conditions, the conventional generators are required. In case of island operation, conventional generator will provide reference voltage for the inverter and allow real power balancing in case of load or renewable source fluctuation. But accurate decision is required to estimate maximum share of alternating renewable source in installed capacity of microgrid generation fleet. If a variable renewable source is much larger than conventional, its output fluctuations may cause instability, since conventional generators doesn't have adequate capacity to compensate imbalance in case of decrease of the output of renewable source. Even if the size of conventional generator is adequate to cover imbalance caused by the variable renewable source, its speed of change of output power might not be enough to compensate sudden imbalance. As a result, the system loses frequency stability. A stable solution can be achieved if energy storage is added to the microgrid. This allows to increase a share of variable renewable sources, compensate real power fluctuations, and increase system efficiency in general. However, a detailed feasibility study is usually required to define the best combination of sources and their sizes, since a trade-off between reliability and economy always exists. To ensure reliable and economically efficient microgrid operation, appropriate control system is always required. There are three possible control strategies. Centralized, it's time-proven, fast and well-developed for large power system, but its drawbacks are that there is a need to establish at least two communication channels, main and reserve, between each component and controller, and the fact that if centralized controller is lost, its functions cannot be implemented. The centralized control doesn't require communication between microgrid components. Most common type of such control is group control, but there is a lack of coordination and optimality in case of such control schemes. The other option is distributed control. Within this scheme, local controllers communicate between each other to reach a common goal. To ensure such communications, there is a need of very extensive information communication network or its wireless implementation. At the moment, such communication is quite slow and not very reliable, but with introduction of 5G networks in the nearest future, the situation can improve significantly. To enhance microgrid reliability, peer-to-peer and plug-and-play operational strategies are offered. The peer-to-peer operational strategy ensures that there are no components such as master controller or central storage unit that is critical for the operation of the microgrid. The loss of higher level may affect efficiency but shall not influence reliability of a microgrid. Higher level generalized controller just ensures optimal goal for all the microgrid actors. Such systems with multiple actors interacting to achieve common control goal are called multi-agent systems, and multi-agent control strategies are a very emerging topic in smart energy world. To allow such control strategy, information channels shall be established between all components. Plug-and-play means that a unit can be placed at any point in the power system without re-engineering the relay protection system. In this case, the protection unit is embedded into each microgrid component. Well, the next topic we are going to discuss is network reconfiguration. Network reconfiguration is intentional change of the grid topology to achieve certain operational goal. Die switches that are used for commutation are usually remote controlled and placed on the poles. If there are many possible topologies, network reconfiguration becomes an optimization problem. Further, we will discuss its formulation. Reconfiguration can be multi-objective or single-objective optimization task. In most cases, it's single-objective. In other words, there are several reasons why a grid operator may want to reconfigure the grid, and one or several of them can be considered at once. There are 5 most used objectives. The first one, minimization of losses. This objective is economical one, since nobody wants to pay for losses, and it's most frequently used. But it often contradicts to the need to maintain certain voltage profile, which requires additional generation of reactive power and thus increases losses. There is a more complex economical objective which deals with minimization of operating costs. It usually accounts production costs, namely the prices of energy consumed from the main grid and from distributed resources. Sometimes maintenance costs and costs of switching are also counted to consider equipment resources. The other objective is characterized by vulnerability indexes and show how close the system to its operating limits. For a node, this limit is related to the voltage deviation from its nominal or specified value. For a branch, this represents its overload factor. One more factor which can be considered is system-wide allowed frequency deviation from its nominal value. So the smaller frequency and voltage deviation and the larger distance from current limit, like shown in the example on the slide, the better. One more objective is also associated with the voltage level is voltage stability index. This index shows how far is the actual voltage level from the minimum one, at which voltage collapse occurs. The last one is the objective associated with service ensuring. It's mostly measured for islanded conditions, when consumption level is greater than generation. If generation cannot match consumption without violating grid constraints, some share of load shall be shedded to ensure power balance. So this objective is to maximize the amount of loads to be supplied in islanded mode. Critical loads may be also prioritized and have different weights in case of consideration of this objective. Since the system variables change in time, the same topology may provide different values of objective function. In fact, to find the global extremum of objective function for a certain topology, it's necessary to adjust controlled system variables. In general case, the solution of network reconfiguration task requires a load flow model and a solver that may utilize different algorithms to find extremum of objective function. No matter which kind of algorithm is used, in general it's a search among multiple possible system states that are estimated with load flow model. The user defines which state variables can be adjusted to search optimum, like real power, reactive power generators and loads, breaker states, transformer tap positions, and etc. And solver varies them according to its internal logic. The output of load flow model are used to estimate objective function and find its maximum mean value among all considered cases. Since objective function shall be estimated for realistic cases only, the optimization task requires to consider system constraints. Among most used constraints for network configuration tasks are the following. Since we consider a distributed network which topology is usually kept radial in order to simplify protection schemes, the radiality shall be checked during optimization. If any loop is identified according to the condition of the slide, this case is excluded from analysis. The rest of constraints are quite usual for all power flow tasks. Load generation balance, generation limits, line current limits, and nodal voltage limits. There are many optimization techniques suggested and tested for network reconfiguration tasks. Hundreds of papers describing applications of these techniques also explain how well they fit in respect to the details of the task. Number of objectives, constraints, size of system, and others. In general, all techniques can be divided in three groups: conventional, like brute force or linear programming and its modifications. Usually these approaches are simple but applicable for the systems with small number of variables. Data structure-based algorithms that search a solution based on binary decision diagrams are used for simplified cases when state variables are not adjusted to achieve optimal solution. And most comprehensive are intelligent or meta-heuristic algorithms, like genetic or particle swarm optimization algorithms. To learn more about these techniques, please follow Smart Energy Systems Optimization course or Artificial Intelligence and Machine Learning course. So that is it for the theoretical part, and then we proceed with the practical part.
The network reconfiguration task will be explained based on the IEEE 15 bus scheme implemented in MATLAB Simulink. A very simple case targeting minimization of losses is considered just to give a general idea of how to solve reconfiguration task. So the objective function is to minimize total system losses, and the constraints are nodal voltages and current limits. The grid normal topology is shown with solid lines, and switched tie lines are indicated with dashed lines. Just 4 alternative topologies are analyzed to simplify the case. These topologies have the line between nodes 3 to 4 disconnected, and one of the lines between nodes 2 and 4, 6 and 4, 9 and 4, 11 and 4 switched on. In initial case, bypass lines are commented and marked with gray color. It might be necessary to change topology multiple times per day, since loads and generation profile changes. So the reconfiguration task shall be solved for all time intervals of the daily system schedule. In our case, we consider just one time interval with fixed loads and generation for simplicity. Because of the same reason, we do not change the state variables to minimize the losses. The 15-bus Microgrid has a connection with the utility in node number 1, so the node 1 is a slack bus that maintains power balance. Besides, we have one distributed generating source connected to bus 3 and having size of 200 kilowatts. Its output is kept constant. The branch parameters and loads are set according to IEEE bus standard data, and the loads are also fixed. To change the configuration, each line is equipped with circuit breaker. The initial status of bypass tie lines is open. To solve the configuration task, we perform load flow calculations to find power losses, nodal voltages, and current flows. All results will be gathered into Excel table for further analysis. Let's start with the initial topology. To do load flow calculations, we need to open Power GUI, then Tools, and click Load Flow. The popped-up window contains bus data of the considered 15-bus scheme. Click Compute. Wait when the calculations is completed, then click Report. We can choose a type of report in Load Flow Report window. Choose MATLAB file report. You can save the report to any folder in your computer. Inside the report file, you can find the values of total system losses, which are necessary to estimate objective function. Besides, you can take the values of nodal voltages to check if they are within the boundaries. Since MATLAB doesn't provide current values in the report, we shall calculate them based on real and reactive power flows values in branches and nodal voltages. Necessary formulas are already added to our Excel file. We just need to take necessary power flow data from MATLAB report and insert into the Excel. You can see that in our case, currents are within considered limits. But the voltage of bus 13 is slightly below lower limit. So we make a conclusion that the constraints are not fully satisfied. In case of a broader formulation of optimization task, we would increase the output reactive power of distributed generator. But in our simplified example, we just protocol the results and proceed with the next topology. Next topology corresponds to off state of lines 3-4 and closed lines 2-4. To change topology, we shall discommand breakers of line 2-4. Change the status. Then turn off breakers of line 3-4. Command them. And repeat load flow calculations. Then create report, save it, and transfer data into the table. The results of load flow calculations are provided in the table. We can see that all the constraints are met. Current constraints, voltage constraints, and power losses are lower than in the initial case. So now we can proceed to the next case. Now we need to do the same for the rest of 3 topologies. In case of topology where bus 6 is tied with bus 4, the voltage of 7 buses is lower than accepted boundaries, and the branch to 6 is overloaded. So the constraints are not met. Moreover, since the currents are increased, the losses are also much higher than in initial case. For the next topology, when bus 4 is connected to bus 9, all the constraints are satisfied, but the losses are higher than in initial case. And for the last topology, with bus 4 connected to bus 11, we have decreased voltage of 7 buses and overcurrent conditions of branch 3 to 11. Thus, we conclude that constraints are not met. But even if we would return the state variable inside permissible margin, the losses are again much higher than in base case. To conclude, topology A that corresponds to open line 3,4 and closed 2,4 ensures the lowest losses among 5 studied topologies. So based on these simple calculations, we may define the lowest losses in case of system reconfiguration. Thanks.